Tonight, I want you to imagine something strange. Imagine that for more than a century, scientists believed they understood one of the most dangerous fault systems in Europe. Not completely, perhaps. Geology rarely offers complete certainty, but enough to draw maps, calculate probabilities, and reassure millions of people that the forces beneath their feet behaved according to rules that had been studied for generations. Then, in 2026, something unexpected happened. Not an earthquake, not a volcanic eruption, not a disaster. Instead, a series of seismic images revealed something hidden deep beneath the eastern Mediterranean that should not have been there. Something no model had predicted. Something that forced geophysicists to reconsider how stress moves through the crust beneath southern Europe. And according to several research teams, the implications extend far beyond Italy. Because what they found beneath the Mediterranean isn't a single fault. It's a chain reaction system. One capable of transferring stress hundreds of kilometers away. And if they're right, some of the largest earthquakes in European history may not have been isolated events at all. They may have been connected. For decades, the Mediterranean basin has been viewed as a collection of separate tectonic systems. The Hellenic Arc beneath Greece, the Calabrian Arc beneath southern Italy, the Anatolian Fault stretching across Turkey, and numerous smaller structures distributed between them, each with its own stress field, each with its own seismic cycle, each treated, more or less, as an individual system. That assumption formed the foundation of hazard models throughout the region. But assumptions are only as strong as the data behind them. And until recently, scientists simply couldn't see deeply enough. The crust beneath the Mediterranean is incredibly complex. Ancient oceanic plates descend beneath younger continental crust. Fragments of vanished oceans remain trapped inside the mantle. Entire sections of crust have been compressed, folded, and stacked over millions of years. Looking at the region with traditional seismic techniques is like trying to understand the wiring inside a building by listening through the walls. You hear something, but you don't see the full structure. Then came the new generation of seismic tomography. Thousands of earthquakes, hundreds of stations, millions of data points. Enough information to construct the most detailed images ever produced beneath the central Mediterranean. And what emerged shocked researchers. Instead of isolated systems, they found long corridors of weakness extending through the lithosphere. Hidden structures connecting areas previously believed to operate independently. Not direct fault lines. Not giant cracks. Something more subtle. Zones where the rock itself behaves differently. Areas where stress travels faster. Like invisible highways buried deep underground. The discovery changed everything. Because stress inside Earth does not move randomly. It follows paths. And those paths appear to connect regions separated by hundreds of kilometers. Researchers began comparing historical earthquakes. The 1693 Sicily earthquake. The 1783 Calabria sequence. The catastrophic 1908 Messina earthquake. Major events in Greece. Even activity along parts of the eastern Mediterranean. Patterns began to emerge. Not perfect patterns. Not enough to predict earthquakes. Nothing in modern seismology allows that. But enough to suggest something remarkable. Large earthquakes might alter stress conditions far beyond their immediate surroundings. Farther than previously thought. And perhaps over timescales lasting decades. Which raised an uncomfortable question. What if some earthquake sequences we thought were coincidences were actually linked? Not directly, not like falling dominoes, but through slow redistribution of stress along deep structures nobody knew existed. To understand why this matters, you have to understand something about earthquakes. Earthquakes do not happen because the Earth suddenly becomes angry. They happen because stress accumulates. Imagine bending a ruler. Slowly, carefully. At first, nothing happens. The ruler absorbs the energy. The force builds. Eventually, one section fails. The ruler snaps. But the energy doesn't disappear. Part of it transfers elsewhere. The same principle applies inside Earth's crust. One rupture changes the balance everywhere around it. Scientists have known this for decades. What they didn't know was just how far that influence might extend. The 2026 models suggest stress transfer may occur across structures much larger than previously recognized. And beneath the Mediterranean, those structures are astonishingly complicated. Some sections of crust reach nearly 70 kilometers in thickness. Others are torn apart. Ancient slabs descending into the mantle contain fractures that channel deformation. Deep beneath southern Italy, seismic waves reveal anomalies that suggest portions of the lithosphere are partially detached, like pages separating inside an old book. These detached sections create mechanical boundaries, and mechanical boundaries control stress, which means that earthquakes occurring in one area may subtly alter conditions in another. Not enough to trigger an immediate catastrophe, enough to affect the timing of future events, enough to matter. And this is where the story becomes even stranger. Because the Mediterranean is not finished evolving. The African plate continues moving northward, roughly a few centimeters every year. That sounds insignificant, but geology doesn't care about years. It measures time in millions of years. And over millions of years, centimeters become mountains. Seas disappear. Entire continents rearrange themselves. The Mediterranean itself is the remnant of an ancient ocean. A survivor. A geological system caught between collision and destruction. Eventually, millions of years from now, much of it may vanish completely. But today, the process continues beneath our feet. Silently. Invisibly. Slowly. And every earthquake. Every volcanic eruption. Every subtle deformation recorded by satellites. Adds another clue. Which is why scientists are increasingly focusing not on individual faults, but on systems. Not isolated events, but interactions. Because Earth is not a collection of separate machines. It's one enormous connected mechanism. And sometimes, understanding that mechanism requires abandoning ideas that seemed perfectly reasonable for decades. The discoveries made in 2026 did not mean disaster is imminent. They did not reveal a hidden supervolcano. They did not uncover evidence that Europe is about to experience unprecedented earthquakes. What they revealed was something equally fascinating. That the Earth beneath the Mediterranean is far more interconnected than anyone imagined. And perhaps the most surprising part of all is this. Those connections have existed for millions of years. Long before Rome. Long before Greece. Long before humans walked these shores. The stress pathways. The buried slabs. The invisible corridors deep inside the mantle. They have always been there. Humanity simply lacked the ability to see them. Until now. And somewhere beneath the Mediterranean tonight, hundreds of kilometers below the surface, tectonic plates continue moving. Slowly. Relentlessly. Quietly reshaping a world that appears motionless above. The science is still unfolding. Researchers are still debating what these newly discovered structures mean for long-term hazard assessments. New seismic arrays are being deployed. More detailed models are being built. And every month, the picture becomes slightly clearer. Not because the Earth has changed, but because, for the first time, we are beginning to see what has been hidden there all along. And perhaps the strangest thought of all is this. The greatest discoveries in geology are rarely about something new appearing. They're about realizing that something ancient was there the entire time, waiting, patiently, for us to finally understand it.